I'm Duncan McLeod, and this is TCS, the TechCentral Show. TCS is brought to you by MTN Business. You can visit them at mtnbusiness.co.za, and we thank them for partnering with the show. Now, long-time readers of TechCentral may remember a podcast and an article we wrote, I think it was about 10 years ago now, with Corrie de Jager of Hydrox Holdings, who at the time had developed a technology that they said had or represented a major step forward in unlocking the hydrogen era. This stuff is well beyond this lowly writer's pay grade, but the claim was this. De Jager and his team had developed a membraneless technique for splitting water into its component parts of hydrogen and oxygen, with the promise of helping the world get to non-polluting hydrogen fuel cell-powered cars and other technologies sooner rather than later. This idea could rather dramatically improve the way hydrogen is produced and lower the costs thereof. Now, a lot has changed in 10 years, Corrie, I'm sure. Technology moves at a rapid pace. Before we get into what you've been up to in that time and some of the advances you've been making with Hydrox Holdings, including what I believe are some significant technological developments recently, just take us through the history of Hydrox, how you got involved in this space, and what the potential is of the technology that you're developing.
Thanks, Duncan, for the opportunity as well. My background was on the legal profession. I've been a lawyer for 45 years, and then I retired some 6 years ago. But prior to that, I was very interested in making some contribution towards making the world green. Mm-hmm. Now, the challenge was always, how can we get hydrogen out of water? Water is plentiful, and there's a lot of hydrogen in water. That's very simple science. But how do we get it out? And this is where we started. A couple of engineers and businessmen, we got together and said, let's take this challenge on. And we started. That was 25 years ago. Wow. So, that was in the year 2000. We started on this, and it was very exciting. And we developed various kinds of units that we can split the water. But eventually it dawned on us this is very dangerous because the hydrogen and the oxygen that you generate from this is a very volatile mixture. So with a spark or even static electricity in the air, you can actually ignite it and it explodes. It doesn't burn. Mm-hmm. So it was quite a challenge to get the hydrogen and the oxygen separated.
But before we get into even any of that, Corrie, your background is in law. You're a former attorney. How does a former attorney or an attorney at the time get into this particular area? What was the genesis of all of this?
Well, I come out of a family where we grew up four brothers, and they're all engineers. I'm the odd one out.
Okay.
I was also entered in an engineering degree, and I changed it. And I said, no, I want to rather go for legal. But my passion has always been being part of doing something worthwhile, and engineering and science has interested me all along. So this was always a challenge for me. We can work and we all do something, but what legacy do we leave behind? What major steps can we do to make the world a better place? Now, this is what drives me, and this is what drives our whole group of directors and engineers still involved in our company. Let's do something major. Let's do something, and do something nobody has done before. Mm-hmm. So we started off, as I say, various units running a car on this very dangerous gas, taking the car even to Fort in Silverton and showing them the car. There was a Mazda Etude, I can remember it very well. And we had a lot of flame arresters because if there's a backflash or whatever, this thing will explode. So we had to stop this explosion. And we had interesting results, 82% drop in carbon hydrates at the back. So your exhaust didn't waste a lot of energy anymore. We had to adjust the timing. So we spend a lot of work, even at Tukkies. We spend a lot of the engineering department running our cars on their machinery there. And we could prove that there is a huge benefit if you add hydrogen to normal combustion. This was not purely hydrogen. It was hydrogen-oxygen mix. And we used the car's battery to give us the power to split the unit. And it was like the size of a 2-liter bottle. that we put inside the car. We use the battery, the 12 volt from there. We split the water into this components, hydrogen and oxygen, and we feed that into the carburetor. But as I say, it's not to be done at home. It can be quite
very
dangerous. So that's how we started. And then we got the message now. Ford tested it for us over 2 days extensively, and they gave us a very nice report. I'll not go into the technical details, but it's fun and games, that we could actually change a lot of things. Your mixture was a 26-1 mixture compared to a 14-1 mixture currently, So there was a lot of potential, but it was too dangerous.
So let's get back to brass tacks here. What is hydrogen, and why is it suitable as a fuel?
Well, hydrogen is an energy carrier, and it's the most abundant element in the universe. It's in everything. As we sit here, everything that lives has got hydrogen in it. And the challenge was always how do you break the bonding, especially in water. If you take water as a medium, H2O, how do you break that to a molecular part to get the atoms out?
So does hydrogen not exist on its own on Earth?
Very few. There is some instances now I think down in Africa, in the middle of Africa, and in France now, they've got some pockets of, they say, pure hydrogen. They call it white hydrogen, but that's still not commercially available, that you can get hydrogen freely. It tends to bind. If you have hydrogen right now here, it'll immediately bind with the oxygen, form water.
Okay.
So you don't have hydrogen freely available. Maybe down in the earth there is some,
trapped somewhere.
Yeah, this is what they're trying to do as well, but not really available. So the challenge always has been, how do you get hydrogen out of water economically?
So is it oxygen that it typically binds to? It doesn't typically bind to other...
No, it binds to a lot of things. This is your steam methane reformation is one process. It binds to, it forms with nitrogen, it forms ammonia, and you can have methanol with CO2. So hydrogen binds with a lot of
things.
Yeah, indeed. But to get it out of water, because water is the most easy one. And the nice thing about it is if you break it apart, you have the hydrogen and you use it through a fuel cell or even an internal combustion engine, which is the new ones they're developing right now. It becomes water again.
Okay.
So there's no wastage of water. This is what's nice about it. The only thing that's wasted is the energy to break it apart.
Yes.
And that is the challenge. How much energy you require to get the hydrogen
And
out.
that's quite significant, isn't it?
Yeah, and I think maybe to mention here as well, Duncan, is that there's no carbon involved in the process. 90% of all hydrogen currently is made through the steam methane reformation, where there's a lot of CO2s generated by means of heating up water or methane, as a matter of fact, to very high temperatures and getting the hydrogen out. But the CO2 is seriously polluting. So they've got to capture that, and that's why they call it blue hydrogen, where you produce hydrogen and you capture it and you store the CO2. But what do you do with the CO2 now? So that's a challenge. But if you take water, it's H2O. There's no C's. No carbon, no carbon dioxide, nothing. So this is why it's a clean, and everybody's going for electrolysis of water. This is the ultimate, the silver bullet, if we can do that. But it was, up to now, it's very expensive. The electricity component is the one that...
How much energy are we talking about here?
1 kilogram of hydrogen, the norm is normally, what is 1 kilogram of hydrogen gives you about 39.4 kilowatts of energy. But how much kilowatts does it take to generate? This is what it's about. Normally 55 kilowatts per kilogram of hydrogen. So you have a 70, 72, 75% efficiency factor.
Okay.
But if you can bring the electricity down to have it more efficient, this is what we're all striving for. This is where I think we now have a huge answer.
Okay. Well, take us through the device or the technology you've patented here and how it works.
Okay. For this past nearly 200 years, electrolysis has been made out of 2 electrodes, and in between you have a membrane. The membrane is like a piece of plastic or a cloth, and that just stops the gases from migrating across to the other electrode. Okay. On the positive side, you have your oxygen. On the negative side, you have your hydrogen. But in between, there's a membrane. The membrane stops the gases from migrating and, again, becoming very explosive. So that's why you must have pure hydrogen. By the way, purity in beyond 94%. If you have for running a fuel cell, you need 99.995% purity, very, very high grade purity. if it's got too much oxygen in, it's explosive and nobody wants to touch it. So that's why to get it, the hydrogen pure is the challenge, and this is what we've managed to do. But again, if you look at the process, you've got the two electrodes separated by a membrane. And that's been done, as I say, for nearly 200 years in the same fashion. You've got two processes. The one is an alkaline, the one is a PEM. And now you've got a solid oxide on the side, which is not really commercially available as yet. But the PEMs and the oxides, the PEMs and the alkalines, as well as the solid oxides, all uses membranes. Solid oxides, very high temperature, above 750 degrees Celsius, up to 1,000 degrees Celsius, and that all uses membranes. That's a ceramic membrane that it doesn't melt. And this is why the challenge was, can you get something done without a membrane? And this is what we did. We started working on the process. Why did we do it, by the way? Because we couldn't afford the membranes. They were too expensive. We said, okay, your process up to now was the liquid that is in between, which is water, and you have some electrolytic solution in there, which is normally KOH, potassium hydroxide, and that is running parallel to the electrodes and then out and in between the membrane, as I say. And one of our inventors, a brilliant engineer, George Anagnostopoulos, the Greek chap, he invented the way, and he said, why go parallel? Let's have perforated electrodes. Instead of going parallel to the electrodes, let's go through the electrodes. So we don't have this pathway along the electrodes, which also creates problems because if there's a lot of bubbles, it stops the current from flowing through. The membrane allows the electricity to go through, in layman's term now.
Sure.
But it stops the bubbles from passing through. So you have on one side, you have the oxygen, on the other side, you have the hydrogen, and the fluid, the water going across with it, and then it's removed by means of a gravitation process. But George changed the process. He says instead of having electrodes that's parallel, we have electrodes that we will go through. So we just use pressure through the electrodes. Pressure from, you've got circumferential flow from around the edges through the center of the electrodes outside. It's like having two pieces of pipe next to each other with a small 1 millimeter gap, and you have pressure all around. The flow goes through the pipes and out. That's all it is. So no membrane. And that's what we astonished the scientific world by succeeding in building these. We built various ones. The first ones were very small. The others are much bigger now, and they all work, and it's a perfect separation. Hydrogen on one side, oxygen on the other, and no membrane involved. So we're very proud of that.
Okay. And then you capture it again using gravity.
Yeah, it goes through a gravitation process. You have lots of marble balls all over, and you break this, the hydrogen and the oxygen. On the one side, the oxygen releases. If you break the surface tension, the water runs down below. You capture it again, you recirculate it. So that's as simple as that. And the gases go up, and you capture it on the top. That's a standard process. That's every single electrolyser uses the same kind of process. There's nothing strange to that.
So what is the significance of what you've done here? What is the significance of this invention?
Well, initially we started off, we have less components. We don't have a membrane. So immediately your cost factor and your longevity will be much better now because you don't have to replace a membrane every 5-6 years.
At a commercial scale, I mean, what are we looking at here? How big are these membranes, these devices for doing this work?
The membranes itself is about 1 meter by 800 meters. And then they
by 800 meters?
800 millimeters.
Millimeters, okay.
Meter by meter. and then you stack them. You have about 66 of them to make 1 megawatt.
Okay.
So they all stack next to each other, and the flow is through them, and this is also very standard. But without a membrane, we have one less component, and suddenly we have less resistance because your membrane also creates resistance, and this is what causes the electricity to go up. But the nice thing about our process is, and that's what we've been working on the last couple of years, is we can suddenly go to areas where nobody could go before. The PEMs or the alkalines, they couldn't go to higher temperatures because the membranes pop. The membranes don't like high temperatures, and then if they break apart or they fall apart, then you have crossover of gases, and then your whole system stops. And this is what you don't want. So suddenly we can go to higher temperatures. Why is that important? Because suddenly you have much better kinetics. You have much better thermodynamic effects. Your current densities increase. You can now, instead of cooling the system, and this is another factor, your cost of hydrogen is governed by two things only. The cost of the unit, the electrolyser itself, which is about 25%. That includes the maintenance and replacement cost of electrodes and membranes. That's 25% of the total cost of the produced hydrogen. But 75%, the bulk, is for electricity. Mm-hmm. Your electricity feed is the most important component here. But unfortunately, due to the current processes used in all these units, there's a buildup of heat, and the heat's got to be removed. Mm-hmm. You can't operate beyond 80 to maximum 90 degrees centigrade. Otherwise, the membranes will start falling apart, and you will have crossover, and you've got to stop it. But to get that temperature down takes a lot of energy. About 40% of your total 75% is heat generation that you've got to remove. So suddenly you have huge losses because of the heat. Electricity that you can't utilize in making hydrogen. That's why your efficiency of the whole process is between 72 and 75%. I'm talking of system efficiency. I'm not talking of only the stack efficiency. The overall efficiency of of putting electricity in there and making hydrogen through a normal process is 75% maximum efficient. So there's a lot of scope to bring the efficiency up. And now we're back to what we have in this country. We have sunshine, we have maybe a little bit of wind, we don't have hydro, but if we utilize that and bring the cost down of the electricity feed, we can bring the cost of the hydrogen down. Mm. Again, practical terms, what is 1 kilogram of hydrogen? The energy value is equal to 4 liters of petrol.
Okay.
So it's based on the American gallon system. How much is a gallon of imperial gallon of petrol compared to what they call it gasoline? Mm-hmm. So again, the 1 kilogram, how much energy do you take to make the hydrogen, and what is the energy value of that hydrogen coming out? So that's where the 70-75% comes in. But now with a higher temperature, we suddenly go where nobody could go before. We can now go to, say, 250, 200, we call it the intermediate range, energy range, electricity range, where we go to 200 to 300 degrees centigrade. And some things change altogether. It's not that hot, interesting. With the solid oxides, they go up to 1,000 degrees centigrade. And that's challenges on the materials. And where do you get the energy? Now you've got to put it next to the solid oxide, now next to a nuclear station to get that high temperature. So what's the sense? Mm. It doesn't make any sense at all. But now with our intermediate temperature range, we can now go to 250 degrees at about 30 bar pressure, which is also a benefit. If you get it at the end, it's already compressed to a certain extent. But the efficiencies, electrical efficiencies, go up to 95%. It's now endothermic. We utilize the heat that's in the system instead of cooling it away. We can use the heat that's already in the system as part of the energy. And that makes it fantastic. And the other nice thing is because of the kinetic reactions of the higher temperature, you suddenly have a 10-fold increase in current densities, meaning a smaller unit can make much more hydrogen, mm-hmm. which cannot be done with membrane systems because of the clogging of the bubbles, and they don't have the kinetic benefits. And suddenly, with the higher temperatures, it just changes everything. A 10-fold increase, a smaller unit can make much, much more, by order of magnitude, more hydrogen than anything else. So that will bring the cost of the units down again. Mm-hmm. So we're very excited about the potential.
So is this working in practice? Have you actually developed this in a?
We've developed just the basic one to prove, and I must give credit to Shell through their Game Changer program. They've sponsored us. And
Shell
in the Netherlands. Yeah, it was quite a challenge. We couldn't mention their name initially, and we were the very first ones in Africa. Ex-Africa, so we were the very first ones supported by them in Africa. And they said to us also the most successful of the whole Game Changer range. So they will probably be also involved in the next phase. So we proved the principle that we can do it at lower temperatures, at 80 degrees, at normal 5 bar pressure. But now to take it to the next level, we have to test that as well. But theoretically, there's nothing in our way. The issues we've got to solve is just what materials are we going to use of construction? Is it polypropylene, polyethylene? What kind of plastics that can handle the higher temperatures and the higher pressures? And then the anode, because the anode is corrosive at the higher temperatures. We've got to look at, is it titanium instead of nickel? Mm-hmm. But these are things that can be solved by the clever guys.
But what does it mean for the commercials around producing hydrogen? How much cheaper do you think it'll be using this new method?
Well, number one, if you don't have to waste 40% of your 75% energy on electricity, on cooling it down, that's a 30% saving on the total cost of hydrogen.
Okay.
That's a one start. So at least we'll say 30% drop in the price of hydrogen compared to what it is currently. So that's a major step. It's not incremental. And then we talk of the increase in current densities. I don't want to venture on that, but of the 25%, suddenly that could be halved, I should think. So, I don't want to speculate.
Sure.
Let's leave that up to the clever guys. There were many studies done already on higher temperature and the benefits. In Europe, especially by the Danish Technical University, we've got the full cooperation. We're using their publications where they've proven all of this. But they couldn't go further with their tests because their membranes popped. They tried to do different kinds of membranes. We don't have membranes. So suddenly these guys are very keen to work with us to test it at the higher temperatures. And if we can achieve a 30% or a 40% saving on the cost of hydrogen, wow, we can compete with fossil fuels.
Okay.
It's going to change the world, and there's no pollution involved.
I was going to ask about the future of motoring here and transportation. I know that Anglo-American, I think it might be their platinum division, don't quote me on that, has deployed hydrogen powered trucks in its mines, and they've been in the logistics industry. I know Amazon uses hydrogen forklift trucks, and I think hydrogen is quite a popular fuel for use in warehouse type environments and that sort of thing. But it hasn't really taken off in the broader motoring industry. I know Toyota years ago built a hydrogen car, and I think it was only ever sold in Japan. You might know the details about that. I know BMW recently has been talking up hydrogen cars again and saying this is the future beyond EVs. Is it purely the cost of producing hydrogen that's holding back hydrogen cars, or are there other factors at play as well?
I think two things here which is important, why hydrogen hasn't taken off. But by the way, it's taking off big time now.
Okay.
Toyota's committed. America has changed to hydrogen now. So the electrical side will still be there, EVs, but that doesn't solve the issues of refilling and the range and then the cost eventually. So hydrogen is now on the verge of exploding. It's just going to happen big time. Everywhere you see it, we get so many inquiries. The two things that affected the takeoff of hydrogen was, where do you get the hydrogen? If you go now in South Africa or in Africa and you say, where do you get the hydrogen? There's only a couple of places you can get it, but most important, what's the cost of the hydrogen? In practical terms, South Africa, you're going to pay 500 Rand per kilogram of hydrogen.
Wow.
That's true, if you can get it. So again, nobody's going to buy it at that rate.
No.
So suddenly we say we can do it at about 120 Rands a kilogram. That's possible. That's even with our standard technology, with we call it the advanced alkaline electrolyser, which is a state-of-the-art system utilizing a membrane. We've gone and we've engineered an electrolyser just to get the cash flow going. A standard system, well, we have many years of experience in this field. So our guys build a standard one where we've got a 20 kilowatt unit that produces 5 kilogram, just a demonstration unit. It's got a zero gap system, a membrane in between, 2 electrodes on the side. And we get very good 72% efficiencies. And this can be done. And even on that one, we can make hydrogen about 120 Rand a kilogram, which is much less than you can buy it. This is now purely at manufacturing cost, not included your markups and whatever the case is. But with the economies of scale, if you do more than one and you start building them a big time, that's going to come down. I mean, there's no question about it. But at this stage, the big manufacturers do not want to make smaller units anymore. ThyssenKrupp, 25 megawatts, they don't want to build small ones. We say, let's build a 250 kilowatt and then a 1 megawatt. That is, 1 megawatt can give 1,000 houses electricity, especially in Africa, smaller houses. So there's a huge demand if we can solve Africa's issues, and we don't have to look to go to Europe and places like that. And in any event, I don't think we can compete with Algeria, Morocco, up there north. They've got all the sunshine, all the wind and all the resources. So how can we compete with them from down here? Transporting our hydrogen by boat all the way up there. And Spain even, they're putting up huge solar plants there.
This was the green hydrogen.
I'm talking of green hydrogen.
Green hydrogen factor.
Absolutely.
That's hydrogen produced with renewable energy.
Absolutely. Africa has got 600 million people who's got no access to electricity. So even Nigeria, our biggest economy, suffers with electricity. There's lots of people that's got no electricity or very bad electricity, even here in our country. I mean, you sit with farmers, you sit with industry, they're moving out because they can't afford this breakdowns. If you can give them electricity all the time, and even so your cement and your steel industries and mobility, if we can have hydrogen stations where you can get your hydrogen, you can run your cars, it's going to change everything. And it's now within our grasp. I'm talking of existing systems that we have, which you can roll out in 12 months' time, but beyond that, the DEF technology, which is going to bring the cost down considerably. That's going to take another 2-3 years. It's got to be developed. But we're confident that can be solved. We're putting a consortium together now of international companies and institutions that has got the facility and the scientists to do it.
So to take us through this technology, what did you call it?
DEFT, D-E-F-T.
DEFT.
Yeah, it means divergent electrode flow-through.
Right.
This is our technology with no membrane, and this is the one that we patented, and we got all the awards internationally as well.
Okay. What are some of those awards that you've won?
Well, it's from the iChemic awards, that the International Chemical Engineering Awards. We got, I think the ones I'm the most proud of is from the Monaco Hydrogen Alliance. They had a forum, and we've been invited now. We've been just made a member of them as well. We're very proud of that. And they gave us, of the 5 awards, we had 2 of the international awards, and we competed against some of the biggest companies in the world. And we got the Best Emerging Technology and the Top 3 award. So that was amazing. And this was handed over by Prince Albert II himself. Mm-hmm. I'm very proud of that, so shaking a prince's hand. So suddenly, the world is now taking cognizance of what we're doing. Mm-hmm. And now it's a matter of us to take it forward, and we're asking people to join us, to get involved, help us. Let's go and change the world, and can be done. Let's make it green. Let's leave a proper legacy.
So where is this going? I mean, is this technology going to be used by big companies producing hydrogen, or do you see a future where I could potentially, as a homeowner, buy this product and install it in my house and produce my own hydrogen to run my hydrogen car and to service my own energy needs? Could we get to that point, or is this only ever going to be produced by big companies?
Duncan, your problem here is the normal homeowner will not be able to afford it.
Okay.
You'll probably, in a neighborhood, you will clock together and you get 10 or 20 or 100 people and say, let's put up an electrolyser and do our own energy. Mm-hmm. Because the bigger your unit is, the less the capital costs. And this is the question. So, and one of these small ones is about $1 million. It's very expensive. So this is unfortunately the nature of the beast. It's not cheap. So if you want to buy it, you've got to stand together and do it. Maybe township developers, yes, they can put it in. And we already get inquiries from that as well. People saying, can't we change, get and work? Because this is the future. If you can go green again, where does the energy come from to split the water? So if you can have enough solar, and again, you're sitting with maybe wheeling, getting the wind from down in the Western Cape where there's lots of wind, that can be done. And we're also in talks with Eskom. So they're very excited about this, and this is what's nice. So things are happening, notwithstanding that we're all a bit careful when we talk about Eskom, but these guys are trying. So we're very confident that there's going to be solutions, and it's going to be green solutions. And Africa can spearhead that.
Mm-hmm. Are there any hydrogen-powered vehicles in South Africa currently?
Not that I know of. The ones that we've seen as demonstration ones, it's the Mirai, the one from Toyota.
So they have brought a demo unit in to test it out in this market.
Yes. And
who's doing that?
I'm not sure at this stage. There's some colleges that were involved in, especially having a bicycle and a golf cart and stuff like that.
Yeah.
I think Highsign in the Cape was at one stage busy with that kind of thing. Mm-hmm. But once you have the hydrogen available and it's affordable, the market's just going to run. The farmers are looking for it. This is big. The mines, they want to get hydrogen down below, because you can run a fuel cell right there in the shaft. There's no toxic fumes, nothing. You've got to, circulate all the air and get it out. It's just fantastic. It's just the answer. But again, where do you get it? What do you pay for it? Mm-hmm. And this is where I believe we have the answer.
Okay. So what are the barriers to the world adopting this technology? Obviously, I imagine you'd want to get the cost of the energy below fossil fuels in short order. And once that happens, there's just going to be natural demand for it. How far are we from that point?
Yeah, it's not really to be below fossil fuels. It's to be close to fossil fuels. Remember, a fuel cell has got a 60% efficiency factor compared to a motor car, which has got about a 30% efficiency factor. So you can get double the mileage, if you want to look at it that way, from hydrogen compared to petrol. So even though you pay a premium for your hydrogen, it's going to give you a much better, distance to travel compared to petrol. So from that, you just got to be close. And this is where, if we can bring the cost down by 30 or 40%, we're already beating the price of fossil fuels. So yes, it's possible, but the trouble up to now was the majority of hydrogen is manufactured from methane, steam methane reformation. It's just hugely polluting, and that's not what you really want. So if we can get it from water, and we believe we're there now, it's going to revolutionize everything. We're on the verge of an explosion into hydrogen and making the world green. It's going to have a massive effect.
What hurdles do you still need to overcome?
Technology, we have to test it. Financial, we've got to get the monies to test it. It's expensive, to pay the engineers and get this done is not cheap. And that's it. But it's solvable. It's really solvable. It's within reach. And we are inviting people to get involved, to get in touch.
So you're looking for capital, venture capital funding at this
Absolutely,
stage?
Absolutely. If we can get that, we can solve the issues very quickly. It's we can short-term build the alkaline one locally. It can be containerized. We can put it on a low bed. You can deliver it where the people want it, and all you need is steam and water, and that's a normal reverse osmosis little machine. And the electricity, which is hopefully renewables. And then you can produce hydrogen. And the nice thing, for 1 kilogram of hydrogen, there's 8 kilograms of pure oxygen, which is currently just bled off. But you can give that to the hospitals. You can make a huge difference in people's lives.
It's a big industry,
With these tunnel farming, the fish farms, they want oxygen in there.
Yeah.
So that's another huge possibility.
Yeah. And the safety issues around producing hydrogen, have you overcome those?
Yes, no, we've been through that. Very good question. Hydrogen is not, if it's pure, there's no risk of explosion at all. And I'm talking of beyond 94%. But we talk of 99.995 for fuel cells. So there's no doubt about it. I mean, you always talk about this blimp, the Zeppelin that exploded, but that never exploded. It burned.
Caught fire.
And it fell to the ground. If that hydrogen was unpure, it would have exploded. There would have been no camera crew down below. There would have been a massive hole in the ground. Nobody would have survived the accident. So it just shows you hydrogen is, in fact, it's flammable with oxygen, but not on its own, indeed.
On its own, yeah. Okay, but the fact that you're separating them at quite close proximity, is there risk there?
No, we've sorted all of that out. Now, and we've got so many HAZOPs that's done on the system itself.
Yeah.
From Shell's angle, they had all these experts coming in, and everything is also done by PLC. So we're sitting with Siemens programs and computer systems. So everything is managed, the flows, the purities, everything. If something should go wrong, and we hope it doesn't, then immediately the system kicks in and stops it all. So no risk at all there.
Okay.
But if you should now mess around with it, yes, I'm sure you're going to look for trouble. That's why we have it enclosed in a container. All you can do is put in water, demon water, and electricity, and that's it. You're not allowed to open it. You're not allowed to mess around with it. And then the technicians will come and service it once in a couple of years' time and replace some of the components as they fall due. But this is what's nice about it. It's actually manageable. For example, if we want to do it quickly in this country, it's a matter of taking the old Sasol model, where you have your filling stations, and you have one central plant where you do it by means of containers. You put it in these pallets. They have all these containers, all these tanks standing there, and about 36 of them, and you put it on a truck and you deliver it to the
like you do gas.
It's gas, exactly. You deliver it to the filling station, and it stands above ground. You don't have to do IEAs and stuff like that. You just put it above ground. It's safer than the LP gas that's been sold inside the kiosk. That's dangerous because that's explosive. If you leak that and you have a flame, it's going to explode. Hydrogen doesn't explode. The test they did on the Mirai is they shot into this tank and they tried to explode. It doesn't explode. Simple as that, because there's no oxygen in it. So, and if it leaks, it dissipates immediately. It's the lightest element of all. So it just disappears. So it just whoops, it's gone. There's no chance of it. So really, we're quite happy as far as the safety aspect is concerned, and we conform to international standards.
Okay, Sasol seems like a company that might be interested in this sort of tech. Have you had any conversations with them?
We had years ago with Sasol, many moons ago. I'm talking about 20 years ago, when we started off. We are way beyond that now. So our system has changed. Our safety is much better. Everything is up. We sorted all of the issues out. We haven't had conversations with the management as yet, because they're making the most hydrogen in the country coming from coal. So, they're selling hydrogen big time, but only, and they use most of their hydrogen themselves, by the way, to change into different kinds of chemicals and stuff. So, yes, they will be interested, because methane is also, what they use from Mozambique. I'm not sure about but you can see the pollution over there in Secunda. It's not nice. So we can change it and make it green. Yes, by all means, we'll be very happy to talk to them.
Okay. Do you, in terms of commercializing this technology, do you see Hydrox becoming a manufacturer of devices that do this in the field, or do you see yourself more like a company like Arm Holdings in the UK that licenses its IP to design chips and has other companies make those chips? Do you see yourself as an IP company that just simply licenses to companies so that they can build their own systems, or do you see yourself building your own systems that you then sell to, I don't know, Toyota, for example?
Duncan, this is much too big for us. So for us to manufacture, we can manufacture 1 or 2 demo units and that's it. But it's got to be done under license. There's no question about it. The demand is from all over the world. We have people saying, can you give us smaller units? Is it immediately available? On the DEF technology, that's going to be massive. And again, we're not limited to 1 megawatt. We can go as big as we would like to. This is what's nice about it. It's scalable. The whole unit is scalable. But as I mentioned initially, it's expensive to build 1 unit. We simply don't have the funding to do it anymore. So we've got to reach out now and say, let's go and do it. But there's no limit. You can go as big as you like. And I think the ideal route is licensing it.
Yeah.
We're already busy with an Austrian-Swiss company.
Okay.
Who's very keen on licensing our technology and doing some of the development work for us over there, which is going to take a lot of headaches away for us because we don't have to worry about that there.
Yeah. Well, I can see your background in commercial law coming in handy when it comes to negotiating those contracts. But you've also said you've patented the technology in various jurisdictions around the world. Which markets have you patented it in? And is anyone else trying to do this?
This has been tried for many years. People have tried to do membraneless, but they've done it on a very small scale, and I can keep you busy the whole afternoon about the various ones. Very interesting what they've done. They haven't succeeded in scaling it up. It's still on lab scale. Even in the UK, there's a company that calls themselves membrane free, but it's a double process. It's not done it on the first step, so it's still not. It's all about energy efficiency. How much energy do you require to make it in the end, and can you scale it up? And this is where we're fortunate we can scale it up. Ours is so simple. People have asked us, how the heck did you guys do it? And this is on an international forum, so where we present our technology. They're just amazed, and it's so simple. This is what's the secret behind it. So yes, we've got it patented in all the major countries right around the world. And we renew our patents regularly, and we have new patents all the time being developed. So yes, it's nice to be part of this and to develop it and to sit and to think. You've got the old expression, think it may be a new experience. And this is what's being done here. We start and we think we've got a lot of clever guys, and they all sit together and said, let's sort this problem out. Don't worry about it's not been done before. Let's look at how can we resolve this. And then we get the answer, and suddenly, there it is. So, yes, we're very proud.
Do you find there's some skepticism as well on the world stage towards a company coming out of Africa claiming to be able to create this world-changing technology? Is there some? Do you pick up any of that when you meet with people, with experts internationally who say, "How the heck could this come out of the dark continent?"
Duncan, Africa does not feature on any of these renewable energy charts anywhere in the world. It doesn't feature. It's nowhere. We remain the dark continent. The first time one of our chips represent one of our engineers we sent to Madrid in Spain. There was a technology challenge, and they said they want to look for green solutions and stuff, but they were actually looking for IP, but IT things. But irrespective, we presented there, and there was about 350 delegates. They had 5 minutes to present their technology, quick 5 minutes. And when he introduced himself and he says his name, and he's from Hydrox Holdings, Johannesburg, South Africa. When he said Africa, 350 delegates turned their heads and look at my poor engineer who's never been in Europe before. He felt like he's out of place. And eventually we got to the final stages. We got through all the elimination routes. It was very exciting, you know. So there's a big bias against Africa, make no mistake. We're not known for our high tech. We're not known for our technology, but bear in mind, I mean, a lot of technology has been developed in this country.
So has it been a bit of an uphill battle to get people to take you seriously abroad?
And now they're taking us seriously, indeed, with the international recognitions and
From
stuff.
Shell.
Shell at first, that's very important to us. And then from Prince Albert, Monaco, you know, that recognition. Mm-hmm. And then from the iChemical Engineering, you know, this is international concerns that come along and give us recognition. But the main thing would be, once we have our first unit that can produce the hydrogen at much less, that's going to really set the world afire. You know, normally your investors come along and they say, okay, I'll invest in your technology. How long before we get a return on our funds? And this is our big thing. There's no real venture capitalist who says, okay, I'm prepared to wait it out. I see you've got the potential. You've done all the homework. You've got all the credentials. We don't get that. We simply don't get it. And you hear all the millions and billions spent on projects all over the show, but it's not about venture capital applying money and taking that opportunity and chance and going through the stages to develop it. They all want a return. And even the ones that claim to be venture capitalists, they come along and they want a return on their monies. And this is where we come unstuck. So we're really looking for genuine venture capitalists that are coming along. Get involved, and right now the potential is enormous.
Yeah. So what sort of funding do you require to commercialize this technology?
To build the AAE, the alkaline one with the membrane in between, that's a commercial one. We'll do it in 2 stages. We'll build a 250 kilowatt one and then the 1 megawatt. We need about 60 million rands. 60 million rands to build whatever. One cost about $1 million itself, just one unit, so just to give you a background, but to pay the engineers and to do all the work that's got to be done. There's a lot of things that's involved here, and again, you will only order one of it, one pump and one of this and one of that. So if you do it economies of scale, the price will come down, and do that and then test it extensively like we did for Shell. You run it through 1,000 to 2,000 hours continuously, 24 hours a day to test it, and then you get the sign-off, and they're happy with it. So this is what's got to be done. And then we've got the blueprints. Then we can actually now say, okay, let's go bigger, 3-5 megawatt, whatever, there's no limit. And you can start opening your order book and say, what do you want? Do you want to buy units or do you want to buy the hydrogen? Because I think the market also lies in people who says, I can't afford that serious 20, 30 million rands for a unit, but I'll be prepared to buy your hydrogen. If you can give it to me cheaper than I can get it locally, say at 200 Rand a kilogram, we still make a lot of profit there. Then it's easy. Then we can do take-off agreements, supply the hydrogen, and your capital is no problem anymore for the consumer. You can buy the hydrogen as he requires it, but certain minimum per day, per month, per year. On the other side, if we do the DEF technology, the one that's got all the patents and the international recognition, that's an open one. I'm not sure how much it's going to cost. We reckon about $5 million because it's going to be done in Europe and in America to a certain extent. And we've got to employ a lot of these universities and institutions. Some is going to do the material sciences. Some is it's got the autoclaves, the high pressure systems where they can test it under pressure and stuff like that. And that can be done, and if we get enough capital behind it, it can be done quickly. I think I said 3 years, but if we put drive behind it and we put our own engineers in there, we can really do it much quicker. We've got Fraunhofer, is the one institute in Germany who's very much interested, and we're in talks with them now. They've got the people available to immediately start on this, and they're very excited about it because they see the huge potential.
People were talking about electric cars probably going all the way back to the 1980s, but it's only they've only really started to take off in the last 10 years and probably largely been driven, at least initially, by Elon Musk and what he's done at Tesla. Do you think that EVs are the future of motoring, or do you think they're just a stepping stone to hydrogen cars?
I think there's a market, there's a place for them as well. But if you want to do the short commute, 50 kilos a day kind of thing, going to town, your big issue is, even now, I read in the papers that some company is spending a couple of billion to put up electrical network here, but they can only do 12 cars at a time per station. a station will cost, if I do my calcs, it's about 10 million rands for a station. You can only do 12 cars you can charge.
And they have to sit there for at least half an hour, probably more.
And this is what happens in the UK. Some of my friends have got children there and they live there, and they've all given the electric cars back because they say there's stress factor. If the temperature drops, like it's getting cold, your battery drops, your battery's performance. So they get this stage fright. They sit there and they worry. It's a psychological thing. Am I going to make it? I mean, this thing is now 20% left, and can I make it? Can I get to the job? And when I get there, is there a spot where I can charge my car? Because although there's a quick charge, you can do it within 40 or 50 minutes. You can take it up to 60 or 70%. But then you've got to get where you can recharge it. Our systems don't allow it. If you look in, say, the south coast of the Cape, Mossel Bay, that area which is very popular in December, if you have 10,000 cars coming down there, all electrical cars, they're going to collapse the grid because they all charge at night.
Yeah.
They each have 40 to 50 kilowatts of energy. Where is it coming from? Our current lines can't support it. So extra energy. So really, it's not, South Africa is not really ideal for electric cars. I think they've got their market. But the main thing is hydrogen, provided it's available and it's affordable. Then it's going to change.
And it's neither of those two things right now.
Yeah. Unfortunately, no.
Is it a chicken and egg situation? I mean, Toyota's been talking about this for years. It has the Mirai, but it only has the Mirai. It doesn't have other hydrogen vehicles. What's really holding this back? Is it the car companies that are not committing enough focus to it? Is it that more work needs to be done by companies like Hydrox to get the cost of hydrogen down? What are the barriers?
I think Toyota itself is now committed. They said they're going to build their own electrolyzers to manufacture the hydrogen for that very simple reason, and then also to bring the cost down. But again, they're limited by science. You've got a membrane, you can't change it. So here we are with new technology that's going to make a dramatic impact there. But again, it wasn't the commitment. They were scared. Is it electrical? Is it not? And you think about electrical in our roads. If you have a car which the whole floor of the car is a battery, and you hit one of our local potholes, think what the chassis is going to do and the battery is going to do, and that battery cracks. Your car's going to burn out. So it's a risk factor, the electrical cars for our roads. We're not really geared for electrical cars, although we'd like to say we are, but it's not going to happen. Eskom is not there to supply all the electricity, so it's a challenge. It's a huge challenge. I think it's nice. They will be there, but hydrogen is much, much easier. And also big trucks. I mean, the space you need for a big battery to equalize a hydrogen car, you can't compare. Trains, there's already trains running on hydrogen in Europe. And so if you can have hydrogen taking our ore from the top there, once our rails are back again, can you think how much we can save? Halfway you have to stop, you fill it up with your hydrogen very quickly and you carry on, especially in the Karoo where you have lots of sunshine, you have your PVs up there, you make your hydrogen, and when the train stops you can fill it up, off it goes. There's a lot of movement going on there, lots of inquiries already. People are seeing this and saying this is the opportunity, this is how we can revive our rail networks again by hydrogen. Provided they don't, they can keep their lines intact, that will help. But electricity can be substituted now.
Why is Musk not building hydrogen cars? Hasn't he said some disparaging things about hydrogen in the past?
Yeah, he said fuel cells is full cells, but I think he's going to eat his words. We'd like to speak to him. I think he's the right guy. He's a brilliant guy. So, and he's South African, so I'm very proud of him. So yes, I think he's pushing his own companies because he's so heavily involved in invested seriously in this. So he can't really turn against hydrogen. But I'm sure he's also coming to see the light. And big companies are changing quickly, and it's just amazing what happens. And you get generators now that's running on diesel or hydrogen, dual fuel. It's amazing. So you can. They already being made. So I'm talking of not fuel cells. I'm talking of internal combustion, like the old Lister engines. They're going to last a long time, and our farmers can associate with them. If you don't have hydrogen, you can go to the polluting diesel, which you all know. But this is nice, and it's 48% efficiency compared to 30% efficiency if you run it on hydrogen. So it makes a huge difference. So hydrogen is really the future.
Right, I'm sure we haven't done the technology any justice in this discussion. I did ask you before the show to keep it at a fairly layman's level. We could have gone in a lot more into the technical details, but for anyone who's interested, who wants to learn, someone who wants to learn more about the technology that you've developed here, how it works, how hydrogen fuel cells work, etc., what's the best place for them to go? Hydrox has a website, does it?
Yes, it does. Hydrox Holdings. You can get it on the website, and you're welcome to contact us. Our detail is up there.
Excellent. Well, Corrie de Jager is the founder and CEO of Hydrox Holdings. Thanks for your time, and thank you for talking to the TechCentral Show today. Much appreciated.
Thanks you for the opportunity. Really appreciate it. Thanks so much, Duncan.